Good evening, everybody, and welcome back to AISC's Night School. This is Stability Design of Steel Structures. Tonight is Session 3, Modules for Learning Structural Stability, presented once again by Dr. Ronald D. Zemian. Today is February 9th, 2015. My name is Brent Liu, and I am with AISC, and I will be moderating this evening's presentation. I want to introduce today's speaker. Welcome back, Dr. Ronald D. Zemian. He's professor at Bucknell University. He received his bachelor's, master's, and PhD degrees from Cornell University. In addition to authoring papers on design and analysis of steel and aluminum structures, Dr. Zemian is co-author of the textbook Matrix Structural Analysis and the editor of the 6th edition of the Guide to Stability Design Criteria for Metal Structures. He is currently the treasurer and was the former chair of SSRC, the Structural Stability Research Council. Dr. Zemian is a member of AISC's Committee on Specification, where he chairs Task Committee 10 on frame stability, and he recently completed his term as chair of AISC's Task Group on Inelastic Analysis and Design. Please welcome back Dr. Zemian. Ron, thanks for being here. I'll hand things over to you.
Oh, great. Well, thanks, Brent, and good evening, ladies and gentlemen, from a wintry central Pennsylvania. On behalf of the Structural Stability Research Council, it is great for Don and I to be joining AISC and delivering this night school course, in which we hope to show how modern methods of structural analysis can be used in conjunction with the system stability provisions of the AISC specification. Here are the session topics for our 8 lectures. And tonight I'll be presenting an interesting opportunity for you in your quest to better understand a wide range of topics in structural stability. And of course, it also gives you many meaningful exercises for better developing your confidence in employing methods of nonlinear analysis. So this is sort of a key slide of what's behind this driving force in looking at nonlinear analysis. Certainly limit states design, we're talking about designing for a structure at its ultimate strength. We know when a structure reaches its ultimate strength, there's going to be significant amount of yielding, significant second order effects, the combination of the both, and the like. So it really lends itself to a nonlinear analysis. And our objective is try to get you folks up to speed and start thinking about how you'll get yourself up to speed. And so the last 2 lectures, in the first lecture I sort of provided an overview of the direct analysis method and how it fit, and then started pointing to the importance of an analysis. The second part of that lecture, I sort of showed you how the computer gets the answer for a linear elastic or first order elastic analysis. And then last week we went nonlinear, and we looked at inelastic analysis and we looked at second order analysis. And again, all trying to show you sort of what the computer was doing. In getting there, I was demonstrating or showing you the results of some software that I had developed called MassTan2. And so tonight we'll also be having a look at that software. I've tried to provide you, for those of you that have been to the MassTan2 site, you'll see that you can also download a textbook. This is a book that I'll discuss briefly in tonight's show. And it sort of it does have some nice chapters on nonlinear analysis, and again geared at the practicing engineer and not at the computer programmer. And so tonight, one more piece of this, and hoping to get you folks to head in a nonlinear analysis direction, is to overview some learning modules. Not only overview the learning modules, but also sort of give you some insight into what you would observe were you to complete the learning modules. So as I think I showed this slide on the first night, steel is a fantastic material. It has great strength to weight and stiffness to weight ratios. We do need to come in at a competitive price, and when we do this, we end up with rather slender members and systems, and slender members and systems are subject to buckling. So you need to be thinking about how you're going to design for stability. Now, just to digress for one moment, I recall my frustrations with stability in trying to teach it. And I go all the way back to a movie I used to watch when my kids were young It was a Wallace and Gromit movie. I don't know if you guys have seen this movie or not before, but it's about these little clay figures, and they get themselves all into trouble, and it's a wonderful ending. But the title of it was The Curse of the Were-Rabbit. And I got to thinking, wouldn't it be great if Wallace and Gromit sort of came forward with a new movie, and it was called Structural Stability and the Curse of the Differential Equation. And what I get at here is a lot of you have taken a course in structural stability or a portion of a course in structural stability, and it's going along well, but then the faculty member or the instructor starts heading in the direction of, all right, if we want to solve this, we need to set up this differential equation, then we need to solve this differential equation. And perhaps your math skills aren't that great, and you're not good at differential equations, and then you make this conclusion that if you're not good at differential equations, you're not good at structural stability. And so that is sort of the knot that I'm trying to untie to some degree with what I'm going to show you tonight. So as I said, the challenge of designing steel structures, a big piece of this is, of course, understanding structural stability. Another portion of it that we're not discussing is the design of connections. AIC has had a couple of great night school courses on that. But back to structural stability, sort of important things is understanding, one, the general behavior, okay? And there's no better way to understand that general behavior than to go into a physical laboratory and start performing tests. All right, so that would be fantastic. Now, it's not always possible to do this, so what I'm going to try to show you tonight is an alternative in which we might be using something what I would call a virtual laboratory. Of course, you can hear all about the behavior related to structural stability in lectures or even reading about it in books. All right, but the thought here is, all right, in order to really talk about structural stability, we can demonstrate the behavior and sensitivity of different parameters on the behavior, but at some point or another we need to make some comparisons against what we might call exact solutions. And so there's two roles to get there. One would be to go through differential equations, and that's a bit of a tricky one because, one, we've got to solve these differential equations, and two, they're often limited by the assumptions related to using differential equations to get to your answer. The alternative, and this is what I'm going to try to demonstrate tonight, is that you could use computational analysis and get there. And once you go the computational route, it's not as limiting as those differential equations and the assumptions can be. So again, what we're after here is getting you to see the forest for the trees, getting you to observe the behavior of structural stability, and appreciate it more and learn from it. And speaking of learning, I have just found in working with my own students, the best way to get them to learn, I don't want to say impossible topics, but more complex topics like structural stability is to get them active, get them doing stuff, getting them running scenarios, what-if scenarios, and seeing what happens. So that's where we're really coming from. Now, it would be great if AISC could send, we estimate that there's a little over 1,000 of you watching the show tonight. If we could send each one of you one of these little devices. They're quite clever, and what we're seeing here is within the body of the device there are a whole bunch of columns, 4 columns. The difference between the 4 columns is the end restraint. All right? The first one is pin-pin, that was Euler. Then we have a fixed-fix column, fixed pin, fixed at the top, free at the bottom. And then what you would do if you had this device in front of you is you'd start stacking weight to find out how much load it takes to buckle the column. And physically you would see the column buckle, and on top of it you'd see the amount of weight that it's holding when it buckled, and you could compare the performance of these columns. And the only thing you're changing is the amount of restraint at the ends, the support conditions. So that would be great. Another awesome one would be, if we could call up our friend Professor Ure down at UT Austin, and he has devices like the one I'm showing in this picture here that shows, how much force it actually takes to brace a member and get it to buckle in the second mode as it's being shown on the right, and how much more force it can actually support. So these are fun little devices, but unfortunately, we don't have access to these, and this would just be one set of experiments. What about all the other possibilities? So this is where this concept of a virtual laboratory came from. To give you a little bit of history but not dwell on it a lot, like I said, There's a textbook that I had the pleasure of joining the late Bill McGuire and the late Dick Gallagher on. And in 2000, we came out with this book called Matrix Structural Analysis. And they had prepared a book in 1976, and we had the opportunity to rewrite it. And when we did, we included several new chapters that were directly on the topic of nonlinear analysis. So it was fun. The problem is when we sort of beta tested the book in the late 90s, not only did our readers conclude, but we also concluded the book was boring. And it was boring because the reader wanted to do what we had done in preparing the figures, and we had run the analysis and showed the results. So in a pretty short amount of time, the two of them, who were in their 70s, looked to me and said, hey, we need you to write a piece of software that can do nonlinear analysis. And so that's where it took off, and it started, and I created MassDan. And unfortunately, Dick Gallagher died pretty shortly into the effort of cancer, but Bill McGuire survived for many, many more years. And Bill and I sort of partnered in this. I'd write the code, and Bill would find the bugs, and we went on. Now, one of the questions that I always get is, what does MassDan 2 stand for? And it's pretty simple. It's literally the first two letters in matrix, the first two letters in structural, the first two letters in analysis, and then the 2 is for the second edition. So it was directly tied to the book, and it was always intended to do that. But it was a strange thing that happened is MassDan became a heck of a lot more popular than the book. Now MassDan, like I said, in the late 90s, it was out there and working. If you Google MassDan, it's kind of interesting. MassDan shows up as a Bengali thriller movie in 2004, so it had nothing to do with that. And in 2005, an Iranian music group became quite popular, and they still are today, called MassDan. And it's absolutely beautiful Persian music, but again, no relationship to my software. But it is nice to listen to that music as you're doing your structural stability analyses. Now, from 2000 really to today, there's been some real interesting developments. First, on the commercial side, more and more programs now, and this came right out of after 2005, and AIC introduced the word analysis into the specification. More and more programs are now providing at least elastic nonlinear options. Several are also starting to provide inelastic nonlinear options. So there's that driving force. Other educational and research analysis has been developed, and it does provide opportunities to do geometric and material nonlinear analysis. And MassDan itself continued to develop, and both we have PC versions and Mac versions, and it is available over the web. And like I said, it's been adopted at many universities worldwide in both undergraduate and graduate, not only analysis courses, but steel design courses. So here's just sort of a quick graphic to show you. In 2007, it used to be available on CD. In 2007, it became available via the internet. And since 2007, I sort of monitor where it's being downloaded, not specifically to you, but your location. And this map sort of shows the world, and the size of the diameter of the circle represents sort of the number of downloads. And so you can see U.S., it's pretty popular, but you can sort of also follow the trends through Brazil or in Scotland or wherever you are in seeing where MassDan's being used. Now, I shot this slide about 10 days ago, and at that time we have about 22,000 versions of MATLAB that have been downloaded that are running just off of MATLAB. The one that's most popular to you all is the PC version, and we've got about 45,000 of those that have been downloaded. But also there is a Mac environment, especially for the younger students in university who might prefer Macs, and so we've had about 6,000 of those. So all said, since 2007, the last 8 years, we've had about 73,000 downloads of MassDan. Now, you would never want to invest in my company because our total income, this isn't profit income, so total income has been zero. So there's much better ways to invest if you're looking to invest. But even since I gave my lecture last week to you folks and indicated would start thinking about MassDan, I could see immediately that in the last week we've had a little over 500 copies now of MassDan downloaded, And so probably the little blip there is a reflection of you folks. So it's exciting to be part of that. Now when you move to using a program like MassDan or any type of program as a virtual laboratory, and you want to start simulating structural stability problems, you sort of need to have a checklist. So I'm going to provide you really two, in this slide, a very comprehensive checklist of just questions. All right, does your program include partial yielding accentuated by residual stresses? Does your program allow for full cross-section yielding? All right. How about local buckling? How about flexural buckling or torsional buckling, or even for a beam, lateral torsional buckling? And if it is this form of buckling, is it just elastic, or can it do inelastic as well? Flexural torsional buckling, what would happen if local buckling wasn't included? Can the program account for initial imperfections, such as frame sway, or frame out of plumb, or even member out of straightness? So two very different types of imperfections. How about second order effects? Can the program handle P cap delta or P small delta? And then will the program actually be able to model system instabilities, either an elastic system instability or even an inelastic instability? So this is sort of the full laundry list. Now MassDan can do most of these, but it cannot do the local buckling ones. And so there's a few on this slide, I think two that relate to local buckling that it can't do. And so maybe there are more sophisticated programs out there, and if you want to study the impact of local buckling on the performance of a structure or on a member, you may need to dig a little bit further than MassDan. So I just spoke to you about the analytical requirements to get there. Possibilities on the commercial finite element side, of course, the big three, Abacus, Adena, and ANSYS, can get you there. These are big programs and very sophisticated and probably a bit pricey for you unless your firm has them. Other ones, Perform 3D, Larsa 4D, Strand 7, SAP 2000. These are programs that are really starting to come forward with their nonlinear analysis capabilities and would allow you to sort of create this virtual laboratory. On the educational front, there's lots of finite element programs that have been developed. Probably a very popular one we see in research side is OpenSeas, a program coming out of Berkeley originally, I think. And then a couple of programs that Don White down at Georgia Tech has been part of, FE++ and GT Sabre, the BASS program coming out of UT Austin, and the list goes on. And so MassDan is just one part of that. So there's lots of considerations in making your choice. Of course, the requirements of what it can and can't do are there, how much you're willing to pay, how available is it to you, the ease of use, the learning curve, and just maybe your own experiences. Maybe you're already using a software package and you want to go back and ask your questions to that software vendor. Can your program do this, that, or the other thing? So here is again my laundry list, and just I run down and I look at, okay, I'm going to need to account for axial stiffness, flexural stiffness, shear deformations. Masking can account for two types of torsion, both the traditional St. Venant torsion, which almost all the programs out there have, and warping torsion, which is this sort of resistance to warping due to something like, say, cross-flange bending. So very few programs have the ability to do that, but if you do find a program that does, there's sort of a nice advantage in studying system stability in that world. Connection stiffness, second-order effects, imperfections, and the list goes all the way down. So I sort of provided you two very comprehensive checklists as you're sort of trying to think about, do we just want to go with MassDan, or do we want to use the Office software and see if we can get there with it? Now, here is kind of a fun slide just to show you. The picture that's currently being shown is what my friend Dan Lenzel, who used to formerly be at Penn State, and Jeff Lehman, who is currently at Penn State, and the way they handle their steel design course when they get to, say, lateral torsional buckling of a beam. So they take their students, and in groups of 20, they take them down into the lab, and over the period of about 40 minutes, they run an experimental test. And the student gets to watch the video, not watch the video, watch the actual test, watch it be loaded, watch lateral torsional buckling occur, and yay, they're done. All right, so they get to see it live, and there's no substitute for that. But not a substitute, but perhaps a complement to that, would be, all right, over on the right, now what I'm showing is a very simple masthead model that we showed could simulate and get very close results to what the Penn State group got in their experimental test in their laboratory. But if you go with this virtual lab approach, then you've got some real nice options. You can have the student do that test, and then they can just change the unbraced length of the member. How much in changing the unbraced length did it impact the lateral torsional buckling capacity? What if I didn't use that W shape? What if I used a deeper one or a less shallow one? A more shallow one? What if the loading condition wasn't a concentrated force at midspan like it is for this test, but a distributed load or end moments? What if the support conditions were different? All right, this beam has been pinned. What if that didn't occur? What if one end was fixed and the other end was pinned? So with the computer, you can turn these things on and off, and then you can really turn on some fun ones that you can't in the lab, and that is you can't tell the beam, okay, don't yield. All right, if you put enough force on there, you're going to yield it. But on the computer side, you can simply say neglect yielding. All right, so you'll only get elastic effects, and then you turn on yielding, and you'll be able to see, how that impacted the performance of the system. Likewise, that beam already has an initial imperfection in it. We can control on the computer side the size of the imperfection, or if we want to include one at all. Again, warping resistance, we can turn that on or off. So to give you sort of an overview of the learning modules, and we're going to take a look at a bunch of them in detail. The objective, again, have fun in solving stability problems. All right. Now, fun isn't like going to the pub on a Thursday night, that kind of fun. But we're engineers, and we sort of define fun differently, and this actually turns out to be addictive and pretty fun. Again, they're intended to be an alternative to experimental laboratory, but not a substitute or not in place of. If you have the opportunity to ever see any type of experimental tests taking place, go there and see them. They are hands-on, and so you are actually doing the tests. And our whole objective is to have you do a bunch of what-if scenarios. I've tried to prepare them in a way that they are software independent. Certainly they will work with Mastan, but if you've got another piece of software and you're up to speed with it, yeah, give them a try. All right. Now all of the modules, and there's 9 of them, have all been prepared in a consistent format. All right, and in each module, and you can download these modules, and I'll show you how in a bit. It starts with an overview of what we're going to look at during this module, what are the learning objectives, what is our method, how are we going to do this. A lot of times while you're setting up the computer model, you might ask yourself some questions here or there, so I'll provide some hints. And I also have a series of questions, and there's really 2 sets of questions. First, the elementary ones that you just did this analysis and you've changed a few things and you're like, okay, what was I supposed to see? And so those are the questions. The questions are very targeted at asking you specifically, what did you note when you did this or that? What can you conclude? There is a section specifically related to those who are using Mastan. And then there's this section called More Fun. And so as if you weren't already having enough fun, well, now we've got this section called More Fun. And really what it was intended for, the modules were originally intended for undergraduate students, and the More Fun were sort of your super seniors or your graduate level students who did want to go the extra yard and check out some more interesting topics in structural stability related to that particular learning module. And so I have found, in working with practicing engineers who have taken on the learning modules, that they enjoy the questions part and doing but they get stuck on the More Fun. They can't stop themselves. And pretty soon I'm receiving emails of suggestions on what more fun I could include within each one of the modules. Some of the resources, they are set up so that you could prepare, let's say, a formal laboratory report or something like that. So I do provide you with spreadsheets to fill in your data. And the other thing that I went into a very sophisticated recording studio in my dining room, and with just some headphones and looking like a complete nerd, I recorded about 2 hours, about 2 hours and 20 minutes worth of YouTube videos, and they're each in sort of like anywhere from 5 to 10 to 15 minute blocks, showing you, one, how to do the learning module, set up the model, or how to include something like an initial imperfection or something like that. So here is an old slide that I took. The learning modules have been out about 3 years, and so here's one in 2012, April 2012. This is right after I sort of finally posted them on YouTube. And again, you'll find them. So if you go to the YouTube and you Google Mastan, well, if you Google Mastan, you may find the learning modules, or you will probably find that Iranian musical group providing their music. So take advantage of both. But I always like to joke with the students, at least my daughters tease me. When I shot this slide, there were 26 views of it, all right? So I had just posted them. I probably just called my daughters and my parents and then my in-laws and asked everyone to just watch it so I'd have a couple of numbers. So I haven't, in this slide, gone viral. But actually, we were just on them for my steel class, and we've got now on Learning Module 1, I think we've got something like 3,700 views. So it's kind of fun to see it taking off and knowing it's not some silly thing that people are watching that a lot of people do on YouTube, but actually an educational thing that they're trying to learn about how to do a structural stability problem. So overview of the learning modules, again, students of all ages. Originally I was targeting undergraduate and graduate students, but I've since really found that the working professionals are enjoying them and looking for opportunities to self-learn about structural stability. And so they get the software Mastan, they get up and going, and it's usually, they don't do them overnight. They'll take one of the modules and, over a period of a week or two, chipping away at it, they'll get enough down that they're understanding what that module is after, and they'll move on to the next one. Courses of all types, steel design courses, behavior courses, structural stability. I've been demonstrating them and using them in workshops, and also even the AISC night school. And in fact, there was at one point when we were working with the AISC night school folks of what should we provide, what should SSRC do? And the organizer and I were suggesting, well, maybe what we should do is take the learning modules and do one each week with the practicing profession, because there are 9 of them, so we could do 8 of them and get there. Everything okay there, Brent? Okay. There are similar versions available. So I'm not saying I invented this or anything. Professor Martini at the University of Virginia uses his software called Arcade. Professor Miller at the University of Washington has a series of programs, one of them called Dr. Frame, and he also has some literature related to them on how you can learn using the Dr. Frame program. So it's similar in context. An important point that I want to emphasize about the learning modules is that the whole point is that they're all based on very simplistic but really accurate computer models. So in the upper right is the Mastan type of models that you would be looking at, and we'll take a look at some tonight. We're talking about modeling, let's say, a beam in this case, just trying to get fairly accurate results. And so I've got 8 line elements. So just 8 elements, very simple model. You'll notice that in the center of this beam, I added some additional elements. These elements do absolutely nothing except for provide you the visual opportunity to see twist. If I had just used line elements and said, all right, it's buckling and twisting, you wouldn't be able to see the twist if they were just line elements. So I added a few, and you'll see this later tonight when I get to a couple of my examples. So we are in no way talking about taking a program like Adena or Abacus or ANSYS and modeling the beam with 3,000 shell elements and really, rolling up our sleeves and going crazy. Not at all. We're talking about using very simplistic models and really learning quite a bit from them. Here is the whole laundry list of the 9. What we're going to do is go through the 9 tonight, and clearly we won't be able to do them, but some will go into a little bit more detail than others. Some will just, hey, this is what this one does, have some fun with it. Others will actually drop down, and we're going to try to do some Mastan analyses. So, all right, to find those learning modules. Some of you have already gone there, others haven't yet, but if you want to get access to the learning modules, they're again at the Mastan 2 website. When you go there, on the left will be some options. You can see you can download the software, you can get access to the textbook, but also you have option to get in there for something called Stability Fun. And in Stability Fun, you can come down and you can find your way into the learning modules, and you can download them or whatever you want to do. And like I said, when you download the modules using what's shown in the red box on the right, you not only get a printout of the module, but you also get the Excel spreadsheet and access to the YouTube videos and everything. I should mention you're always looking at people's computer screens. Across the top you can see my interest of my bookmarks, Google and Google Maps and all of that. But over on the right is a website called Mech Movies. And this is a program that's developed by one of the folks who are actually watching the webinar tonight, and we've been emailing back and forth. And if you really want to go back and get an excellent education in solid mechanics, Professor Tim Philpott has put together some real nice software for you called Mech Movies, free, and I would really invite you to head there. So put a circle around that part of the slide, upper right, Mech Movies, and go find it. All right, so let's have some fun with the first one and just show you how they're set up, and we'll use a pretty simple one. So Learning Module 1, Elastic Column Buckling and Effective End Restraint. All right. So what I'm after here is a few things. One, getting the student up to speed and looking at some buckling problems. We do know from differential equations, we already know the theoretical elastic solution, so we can compare our computer software, make sure we're getting the same solution, so we're getting some confidence there. We have a reason for doing this. We want to see what is the impact of end restraint on the buckling capacity and the buckling shape. And of course, it's always fun to go to that table in AIC and have a look at the K factors. All right, so this is the table that many of us have seen. It appears in the commentary. It's basically showing you what happens. And we've got 6 columns here, and each one of these 6 columns are theoretically identical. The only thing that's different in them is their end restraint. Okay. The first one, we have no end restraint at the top and bottom. We have no rotation at the top and bottom. Second one, no rotation at the bottom, but it's free to move at the top. And we can move all the way across and look at all these different boundary conditions. And from them, they'll have an impact, of course, on the buckling strength, which in turn can be represented by an impact on the K value, or the effective length factor. Now, before we sort of would dash off and start doing this with Mastan, one of the things is sort of a warm-up exercise, and that is included in this module. And sort of answering that first big question, all right, I'm going to use some finite element software, in this case Mastan, to model these. How many elements do I need to model the compression member? And so what you would do is you would start with, okay, I know the theoretical solution to, let's say, case A, no rotation top and bottom, and you'd use one element, and you run the program, and it comes back and it gives you the buckling load, and it's nowhere near what you had theoretically been able to calculate. So then you use 2 elements, and you keep increasing the number of elements, and you'll find 2 elements is going to get you within a few percent. 4 elements, you're practically on top of it, and certainly with something like 8 elements, you're within a whisker of the buckling load. So that's sort of the first thing, again, getting you the feel of how many elements does your particular piece of software need in order to start calculating the buckling strength of members. So we're going to give this a try. What I've done for you tonight is we're going to leave my PowerPoint presentation, and with a little luck, we're going to come into Mastan, and I'll just sort of run the example for you. What we have got here is, again, those 6 columns that I was showing in the previous slide. And what I've done at the top and bottom, you can see the columns representing them by 8 elements. And I've got different boundary conditions. So these red arrows imply restraint. And so you can see this particular one in the lower left is restrained from moving up and down. Well, of course, we need to resist the axial force. But it's also restrained from moving left to right, and it's also restrained from rotating. And if we move all the way across, we can see the first few were what we would call fixed support conditions. Then I have a pinned support condition, then a fixed support condition, and then a pinned. And then coming across the top, I need to, of course, permit vertical movement so I can actually buckle the column, but I've got different possibilities on the amount of horizontal restraint. These have horizontal restraint, the third one doesn't, the fourth one does, the fifth one doesn't, and then also different amounts of rotational restraint. And what I'm doing by changing those boundary conditions is I'm back to getting the boundary conditions that are consistent with this picture that I was showing you before. Now the next thing I'm going to do before we drop down is just let you know that on the top of each one of these columns, what I have put is a 1 kip force. And the reason I used 1 kip is because a program like Mastan is going to report the buckling load ratio. And so if the buckling load ratio were to come up with the number 100, then I would know it would take 100 times the 1 kip force on the column to buckle the column, or it would take 100 kips. And so we'll go through and give this a try. So here we go. Let's see. Now, I've got another computer in my office, and I'm having a look at. So what you should see at this point is the Mastan software. Again, it's menu driven. We've got pull down menus from the top, file for input and output. It's a 3D program, so we've got viewing options and turning on and off labels and the like, geometry, the ability to create the models. Now, I'm not going to do that tonight. I think it'll be more fun just to see the results. But that's where, if you're nervous about, oh, how am I going to create that model? I don't know how to use Mastan. If you go to that YouTube video, in 15 minutes, you'll be up and running with Mastan. Properties, we need to define the section properties and the material properties, the conditions or the boundary conditions, the support conditions and the load. And then finally, we've got a whole bunch of different levels of analysis, and one of those is to actually do a buckling analysis. So I'm going to come down to elastic critical load here, and I'll pick that. And then down at the bottom, it's asking you how many modes do you want. Well, I want to buckle all of these columns, and so just for fun, I'm going to run the number of requested buckling modes up to 10. Now you might say, well, how did you know you needed 10 and not 20? Well, I've sort of cheated and already done this before. But if you don't have enough, you go back and you just run a few more. And it doesn't take very long to run the analysis. It just ran in a split second, so it's not the end of the world if you have to go back and increase the number of buckling modes. But if we come out over results now, and so we can plot things like deflected shapes and axial forces and the like. So let's plot the deflected shape. And the first one we're going to plot, and so down at the bottom here, you see the number 1, and that means the first mode. And I hit the apply button, and it draws the first buckling mode. And you can see that first column is buckling, and buckling load ratio may be a bit small on your screen, but it says 273.6. I had 1 kip on there, so that column would buckle at 273.6 kips. It's the first mode. It buckled at the lowest amount of load, which is consistent with the fact that it had the smallest amount of rotational restraint. And then what we can do is take a look at the second mode. And so there's the second mode. Interesting. It's the same buckling mode as the first one. And the student starts to think, oh, wait, yeah, the second column there that buckled, the one that's buckling right now, is actually the upside down version of the first one. So that sort of makes sense. And then we can come over to the third one. Well, finally, we're at the third one, which is the Euler buckling load at 1094. And we can go to the fourth buckling mode. All right, now we're still at 1094, so this is rotation top and bottom, but allowed to move at the top. And that's the same buckling force. And I go to the fifth one in the fifth column. So we've been sort of working from right to left. We've now got this column buckling and its value. And then we're thinking, okay, one more mode, and we should see the first column. It's the sixth one to buckle. So I go to the sixth one, and no, the first column still hasn't buckled. And in fact, now we're into a higher mode in that column on the right. So then we go to the seventh. Nope, we still haven't buckled that first column. The eighth, oh gosh, now we've got the Euler column buckling in its second mode. And students often ask, well, why would I want to know that mode? And of course, you just grin and saying, well, if you needed to put some bracing in a column, where's the best place to put it? And it's just begging for the student to answer mid-height. Go to the ninth mode. And finally, at the ninth mode, at buckling load ratio of 4380, all right, which is actually 4 times that of the Euler buckling load, we have finally buckled that column. And that's the column that had the most rotational restraint. So we're going to jump back over to here. And so like I said, we can get the buckling mode. And what we're doing is something very consistent with what was shown. If I could send out each one of these tests to you, we've done that very similar test. Now, a little bit of math that I'm going to show the final answer on the next slide is we know that the critical buckling load is what Euler gave us, the elastic critical buckling load of pi squared EI over the effective length squared. The effective length, the buckling length, is K sub K times L. So if we take this equation, set it equal to P critical, we can actually back solve for the K factor. So from the buckling load, we can get the K factor, and then with that K factor, we can compare it against what AISC is documenting in their table. And sure enough, I'll move right along through these slides. Here was that first mode, buckling at 273. Take that buckling load, EI over it, square root pi over L times it, and I've got a K factor of 2, and that's what's being reported in the commentary. And then we're just going to continue to do this for each one of the modes. And third mode, that is actually the Euler buckling mode, pinned at the top, pinned at the bottom. The fourth mode, the fifth mode, and then finally sixth mode, nothing, seventh mode of no concern, eighth of no concern, and finally we get to the ninth mode, and we get that K factor of 0.5. Now, like I said, each one of these sections has a more fun part to it. And in this case, what we would be actually doing here is having the student not use a pinned or a fixed support at the bottom, but actually provide a beam, across the top or bottom. And in this case, I've required the student to make the moment of inertia of the beam at the top and the bottom to be equal. And then what we can do, as this plot is showing, is we can vary the moment of inertia, and we can watch what its impact is on the buckling load of the column and what its impact is on the K factor in the column. So kind of fun stuff once you get used to it. Now, that is requiring, the first part, we require the student to use the same moment of inertia, top and bottom. Well, what if we are allowed to use different moment of inertias, top and bottom? Well, now we're into sort of a 3D plot looking at the buckling load and the K factor. So, boy, now you're really having fun. The second learning module, so break here for some questions in a minute, but let me just get on with it, is looking at factors that influence the flexural buckling strength of a compression member. So now what we're going to do is pretend we go down into the lab, and we're going to test a bunch of columns that have different slenderness, different L over R ratios, and we're going to turn on and off factors like initial imperfections and residual stresses, and we'll create a column curve or a bunch of column curves, and then we'll compare them against the AISC curve. And what the students begin to see is something like this, and this is coming out of Radal Bjehovd's PhD thesis at Lehigh, is that the AISC column curve is one curve, but when you actually look at a wide range of experimental data and prepare a column curve, it's a bit of a Milky Way, especially in that medium slenderness range. So here we are. The learning module is again looking at a whole bunch of different L over R's, range slenderness ratios ranging from 5 to 190. And we just look at a whole bunch of different cases, and when we get to the computational, with imperfections but no residual stresses, no imperfection and residual stresses, blah, 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 all the way down. And from that, and going into MassDan, we can get column curves, and we can compare these column curves against the AISC column curve. So the AISC column curve is the one in green here, and the other column curves are, like I said, the variations of when you have initial imperfections turned on or off, or residual stresses turned on and off. So you're really running a virtual lab. Another fun one is the Learning Module 3, where you sort of start to look at system stability, elastic buckling and inelastic buckling, and calculating K factors. And the students not only calculate the K factors based on like what I was showing you in the first module, but now you're in systems. And so where would you get a K factor otherwise? Well, you would go to the alignment charts. And then you start to look at all those assumptions in the alignment charts, and you start scratching your head about whether you want to employ the effective length method or do you want to just use the direct analysis method. Now, directly parallel to that Learning Module 2, where we looked at factors influencing the strength of compression members, we can also generate beam curves and look at factors that influence the strength of flexural members. So now what we're going to do is look at a whole bunch of beams of different lengths, and we'll look at their bending capacity as the unbraced length of the beam changes. And then we'll turn on and off factors like yielding or initial outer straightness, and we'll see how that influences the lateral torsional buckling strength. And of course, we know from Chapter F there's a beam curve, and we'll make a comparison there. And this is, in fact, the sister to the second learning module. So there we are. You can see I've taken the beam and I've turned it vertical just so it fits on my slide, but we don't have axial force on it. We have equal and opposite bending moments on there, so the beam is subject to uniform bending, and away we go, looking at all these different cases. And so this is just one example of showing when the beam would fail and what it would look like. And here are the beam curves. So in this case, along the horizontal axis, we no longer have slenderness, but we have unbraced length. And on the vertical axis, I've taken the capacity computed either by AISC or by the computer and normalized it by the plastic moment capacity. And we can see that for relatively short unbraced lengths, we can reach the full plastic moment capacity. And then for this mid-range, we get inelastic lateral torsional buckling, and then finally we get elastic lateral torsional buckling. And in each one of these ranges, we can see what the effect was for things like imperfections or the like. So Brent, I think I'll stop here and see if you've got any questions for me.
Okay, thanks, Ron. We do have a couple questions. And just to let you know, I think we're really good on time, so we'll answer a couple questions and then move on from there. First question, for the simple column example that you just went through with Mastan, did you enter the initial imperfections, or did the program set the initial imperfections?
Okay, great one. The way we would do that in Mastan, and again it varies from program to program, is there's sort of two ways. One is the brutal way, and that's to just go in and brute force, pick a node and move it over a small amount, and then take the next node and move it over a small amount. So we could do that, but we don't need to. Probably the easiest way to do it in a program like Mastan is to do a buckling analysis. Now we would have the buckled shape, and then there's an option in Mastan to update the geometry to reflect that buckled shape. And so what would happen is you would change the original geometry of the column, and it would scale off the buckled shape to include the whatever size initial imperfection you wanted to include. And again, there's a YouTube video on how to do that.
Okay. Next question. Can Mastan handle torsional effects on unsymmetric sections such as an angle?
The million-dollar question. No. Mastan has some pretty decent facilities for calculating torsional buckling, all right? But when it comes time to actually modeling angle behavior, angles are a really difficult thing to get there. And so we can approximate the behavior, but to actually get that flexural torsional buckling of an angle, that's a tough problem to do. And Mastan can get you close, but it can't get you all the way there. And I'm actually not aware of any programs commercially available that can do something like an angle. I think if you're going to go the angle world, you're probably going to step back and model use shell elements and actually model the angle and its length. But perhaps somebody will type in a question tonight and just tell us some other software that can do it. But I'm aware of some research programs that can. A program, for example, that's been developed at the University of Sydney by Greg Hancock. But these are pretty high-end programs. I'm not aware of any that are commercially available that can just do it on the fly.
Okay. Then one last question. Can you go to slide 22, please?
Yep.
One question came up. Can you explain what CU-FSM is?
Sure. I didn't see it. Actually, I'll hit that at the end.
Okay.
It'll come up again on my last slide.
Okay. So why don't you take us back to slide 52. And we just had a couple comments, Ron, that transitioning through the slides was a bit quick. So
okay.
Just slow that down just a bit, please.
All right. Surely.
Right,
okay. Good. So this next one I'm actually going to slow down and methodically walk through with you. It's a real fun one. And what we're going to look at here is lateral torsional buckling. We're going to keep it simple and study elastic lateral torsional buckling. So for this example, we're not going to consider yielding. But certainly once this is done, and you can almost imagine in the more fun part, it says, okay, let's go material nonlinear and repeat the same study. And that gets really interesting. But just to get us up and running, what we're after here is we know that we have a theoretical solution for elastic lateral torsional buckling of a beam when it's subject to a uniform moment. So that means it has equal and opposite moments at each end of the beam. The beam, if you were to draw the moment diagram, it would just be constant all the way across. And when we have a nice, happy, elastic solution to that. The question then comes is, what if we have any other type of moment gradient on there? What do we do? And in many specifications, the rule is to adopt a moment gradient factor, or a C sub B, and scale your solution for your lateral torsional buckling up by the C sub B factor. All right, so that's what we're after. And so here is a picture that is taken out of the AISC commentary, and it's showing you that if you have uniform bending, you would basically come across this on the horizontal axis is the unbraced length, and if you had uniform bending, you'd be at the full plastic moment capacity up to a certain unbraced length. Then you would experience inelastic lateral torsional buckling, and then finally at a certain length you transition into elastic lateral torsional buckling. Now that curve that appears here in the equations that AISC give are for the basic formulation, and that is a uniform bending. All right, that's not for, so it means that the moment diagram is constant all the way across. Now for any type of non-uniform bending, okay, then you would be permitted to scale up your results by a C sub B factor and increase your bending strength. As long as you don't go above M sub P, you can increase the strength for uniform moment by a C sub B modifier. So that's what we're going to sort of study is, how accurate is the C sub B factor AISC provides, and what does a computer program looking at if we were to back calculate a C sub B factor from it. Now this learning module looks at a bunch of different cases. We're going to focus on case A, where we just change the amount of end moments. Okay, but certainly we could look at the case where we vary the concentrated force along the length of the member. I was showing you the Dan Lenzel test at Penn State where that concentrated load was at mid-span. And then of course we could also do the same study using a distributed load along the unbraced length of the member. All right. And in each case, the AISC C sub B equation is provided right there in Chapter F for you, and that's what I'm showing down here. And basically how they get C sub B is they sample the moment at different points along the beam, and then they sort of come up with this equation, and Bob's your uncle, you've got a C sub B factor. So if we take a look at the top slide here, what I've done is, again, used a model. I was showing you this one earlier, in which I've subdivided the beam into 8 elements. I've added a few additional elements in the middle just so you can see the section twist. In this first example on the top, I have subjected it to equal and opposite end moments of 1,000 inch kips. If we were to plot the moment diagram for that, we would have a uniform moment diagram. I do my buckling analysis, and I would get a buckling load factor of 3.6. And 3.6 times 1,000 would tell me that the computer is indicating that we would get lateral torsional buckling at a value of 3,600. All right? And I provide you then the textbook solution for that. And so you plug your numbers into the textbook solution, and you get 3,600. So this is catching that effect. Now what we can do in the bottom screen is we can take, let's say we keep the moment at the left end the same, 1,000 kips, but at the moment at the right end, maybe we switch its direction and we don't make it 1,000, we make it 600. The result now is that the moment diagram is significantly different. It's now a non-uniform moment diagram. It changes from the left end to the right end. It's linearly changing, and in fact, on the left end, the top of the member is in compression, and on the right end, the bottom of the member is in compression. So we're off and running, and we can compare what mass tan. So we do our buckling analysis. We get the buckling critical load to be 9787. And if we divide that by the 3601 from the top case, that's sort of the C sub B that a computational analysis would be finding. In our case, it's 2.7. Now, if you go to the AISC equation, you would get 2.2. So, okay, well, AISC equation is conservative in this case. So it's just kind of showing you the capabilities here. So what the student would do then is they could run a wide range of different moment ratios going from equal and opposite end moments. That would be one end to the other of a -1. That was the first case. And then they can go all the way out over to the equal, literally moments in the same direction and equal value. So that would be full moment gradient with an inflection point at mid-span. And again, taking those ratios, we could see what mass tan gets, and that's what's being shown in the red. And then we could see we could plot what the AISC C sub B equation would give you. And it's kind of curious because everything's going along pretty well until we start getting to these moment ratios where AISC is saying, hold on, just go sort of slowly and flat across, where the computer is saying, you know what, you've got a little bit of extra strength out there. And so you might be inclined to go and find a paper in the AISC Engineering Journal, a 2010 paper that was by Wong and Driver, and excellent paper that goes through all the different C sub B factors that are out there, Canadian code, AISC code, the British standard, the Australian, the Euro code, and it plots up, and then all their computational analysis, and it plots up all the different C sub B factors as you change that moment, those moments at the ends. And you get a feel for where mass tan checks in and where the codes are, and then you can see the most conservative of all of them sitting across the bottom is the AISC curve. All right. All right. So now we're having a lot of fun looking at other codes and the like. So let's give this a try. Like I said, it would be awesome if I was sitting in your office right now next to you and the two of us could crank this up. But just short of that, I'm going to try to lead you through this exercise. What we're going to do is we're going to take a W24 by 68. It's 24 feet long or 288 inches long. And we're going to do some mass tan with it. All right. And we're going to look at some different cases. And I just wanted to again emphasize that for uniform bending, all right, equal and opposite end moments, the top flange, the top of the member, all the way across, has the same stress in it, same compressive stress. We have a uniform bending moment diagram. The critical lateral torsional buckling moment that would produce this is 300 kip feet, or we'll be comparing it in kip inches, so that's the units that mass tan are working in right now, so 3,600. So that's sort of our base value. Now, to give you a feeling of sort of the fun that you can have in this learning module, we don't stop there. We're going to do two things. One, we're going to change the end moments. In one case, we'll have the end moments so it produces uniform bending across the member. And in the second, we're going to change the end moments so that we have non-uniform and we'll have equal end moments at each end. All right. So those are those ratios at the two ends. And then just so we can have a bit more fun, what we'll do is, of course, in all cases, the ends of the member will be braced against twist. But we'll also go in and brace, in case two, we'll also go in and run analysis for what happens when we have braces, a brace at midspan and at the ends. So we can study not only the impact of having, in this case, an inflection point along the length of the member, but also what happens when we introduce a brace. Now I'm going to drop down and show you the mass tan model. But you all have this slide printed out, and it's a bit of a map because what I decided to do is create a mass tan model similar to that column model before, in which I'm going to have 5 beams now, and each one of these beams are going to be slightly different. All right. So let's walk through the beams. Starting from the back beam, all right, the furthest one, I think I'm pointing to it now. You can see my cursor. That beam is being subject to uniform bending. All right, so we've just got a constant moment diagram all the way across. But I have purposely turned off warping resistance. So this beam could never be manufactured, but it literally has no resistance to cross-flange bending. All right, so the only resistance in the torsion term is GJ. It has no C sub W. And then what I wanted to just show you for fun is what the impact of just turning on the warping resistance. So in the second beam, which I'm now pointing at, or the orange arrow is pointing to, that is the case where we have uniform bending, braces just at the ends, and it's being subject to, and the beams has its full resistance, both same for non-torsional resistance and cross-flange bending or warping resistance. So we get to see how important that C sub W is and why those wide flange sections are pretty nice to use. The next beam then is same before. We've just got bracing only at the ends. We do have warping resistance turned on, as it is for all the other beams now. And what we're going to do is subject this one to non-uniform bending. So we're going to have equal moments at the end, and we'll have that non-uniform bending moment I was showing you before. Then we go to the this beam here that this, I guess it's like a light blue is pointing at. This one, we're back to a uniform bending, but we have a brace at mid-span. And then finally, we've got the last one in which we've got the best of both worlds. We've got the brace, and we've got non-uniform bending on there. We have equal end moments. So those are the cases. And I think at this point, I'm going to try to drop down into Mastan. And let's see what all happens. Now it will take me a second to open the file. All right, so here's the Mastan model, and like I said, I've got the 5 beams. Let's go in. We're going to run, again, you can see all the different capabilities in Mastan, but we're going to go back to that buckling analysis just for tonight. So elastic critical load. Now I played with this one, and it took me a lot of tries. I was actually surprised, but it took me up to 15 modes, calculate 15 modes, before I could actually see them all the ones of interest. So some trial and error here. The short story is it takes 15 to get there. And hit apply. Now this analysis is not quite as snappy as the previous one. The reason being is the previous one was really a 2D analysis, where now we're into 3D. But okay, we're done. And so let's go over and have a look at the diagrams and the deflected shape. And we'll plot up the first buckling mode. And you can see the first buckling mode is occurring in the first beam, the beam all the way at the top here. And it's at a buckling load ratio, I don't know if you can read that up at the top, but of 2.26. And again, we've got 1,000 inch kips of moment on each end. So the critical buckling load here is 2265. And you're like, well, wait a minute. Our theoretical solution, what was that? That was something like 3,600. Why are we so low? And again, that was the beam that I didn't include the warping resistance on. So Mastan does have the ability to account for warping. And in this type of problem, warping is your best friend. So let's take a look at the second mode. And in the second mode, we can see that lateral torsional buckling occurring in the beam. And up at the top, we can see that the buckling load factor is indeed 3.6, or multiplied by 1,000 is 3,600, and that's the textbook solution. And then, like I said, we can start moving through the modes. And this is kind of fun we want to see how much load it takes to buckle each one of these 5 beams. We've done the first 2. So we need to start hunting through the buckling modes. Here's the third one. Third one's not very interesting because we're back to the first beam. Fourth one, still in the first beam. So we keep buckling that first beam, and that's because it doesn't really have as much torsional resistance. Fifth beam. Finally the 5th beam now. We've actually, 5th mode, sorry. We've finally buckled the 3rd beam. And again, what this beam was is we had moment gradient. We had equal moments at each end. We had that non-uniform moment diagram with an inflection point at mid-length. And it took 9.8 times 1,000, or 9,800 inch kips of moment to buckle this thing. 6th mode, Oh no, we're back to the first beam. 7th mode. Oh, okay. Finally in the 7th mode now, we've got the 4th beam buckling. And in this case, we get a nice happy buckle shape. It's pretty much what we would expect. Again, the middle of the beam is braced from twist, so it can't rotate. And what we basically got is 2 beams buckling. But it is a continuous beam. All right. The load factor there was 12.1, so it's taking about 12,100 kips to buckle this thing. And now it gets a little more fun. We have to go searching, and I don't think I'll waste your time. I'll just sort of give you the punch here. Is I think I had to get all the way, I believe, the 14th mode. Let me go up and see what the 14th mode looks like. Nope, 14th still isn't there. 15th mode. Okay, so finally at the 15th mode, I was able to buckle the 5th beam. The 5th beam, again, is braced at mid-length and was subject to a non-uniform moment. So we had equal end moments at the ends, giving us that non-uniform bending moment diagram. And that is a buckling load factor of 27.4, or it would take, M critical would be 27,414 inch kips. So let's jump out of Mastan and back into our PowerPoint. Now, realizing that you probably wanted to sort of save those screenshots, I have imported them into this PowerPoint presentation. And again, this was the first buckling mode, and it didn't include the warping resistance. And so we've got 2200, where we were really looking to get 3600. So now we get to go from 2200 to 3600 by including that fact of when we have cross-flange bending, which is actually real, is there, and we get that warping resistance, and it's helping us. So you can see I'm going to start filling in that table up across the top. So that was case 1, uniform bending. Case 1 meant only braces at the end, but now non-uniform bending, we got up to 9,800. Now we've got a brace at midpoint, uniform bending, we're at 12,000 inch kips. And then finally the last one, which took us all the way up to mode 15, we have non-uniform bending and a brace point at the middle, and the buckling capacity is 27,414. So we've filled in our table, and now it would go to time to answer those questions. And if we sort of work across for the uniform bending case, all right, so for uniform bending, what happens when we put a brace at mid-span? And for uniform bending, when we put the brace at mid-span, the student would find that they have increased the elastic buckling capacity by a factor of 3.4. So what they really did by putting that brace at mid-span is they cut the unbraced length in half, and this had a big impact on the capacity of the beam. So L sub B was significantly reduced, and they got a bump up. The next one then was, okay, well, what happened when we move from going from a uniform bending moment diagram to a non-uniform bending moment diagram? And in doing that, life was good. We got an increase in capacity of 2.73, and that again is what that C sub B factor is intended for. So then the last one is what happens when you have a moment gradient, say in this case an inflection point at midpoint, and bracing. And that's where you go from 3,600 to 27,000, so a factor increase of 7.6. So this is significant, but it's a very important point that the student and you folks need to understand, is that just because we had an inflection point in the beam, yes, that increased the capacity, and we accounted for that with our C sub B factor, and we got to 2.7 or 2.2. But an inflection point is not a brace point. A brace point pays off huge, and you get not only the inflection point increase, but you also get the unbraced length being significantly reduced. So the takeaway then for the student in this one would be an inflection point is not a brace point. Okay, I'm going to have to move along at a slightly quicker pace, but Learning Module 6 is all about going back and designing beams, and we're going to design the beams using the elastic procedure and also plastic design. That's what it originally was called, or now inelastic analysis. And of course, we also know that AISC has a 9/10 moment redistribution allowance, so how does that factor in, and how can we use it? All right, so here would be all the cases we look at. So I've taken a sort of a continuous beam fixed at the ends with some support points and a concentrated load. And then I start having the students try all different scenarios of a concentrated load or trying to come up with the lightest beam possible using both elastic and inelastic analysis and AISC's 9/10 rule. And off we go, and we're having sort of a blast with that one. And I think I was showing some slides last week of plastic hinges forming. So here are the results of plastic hinges and the benefits of using an inelastic analysis. Learning Module 7 is a neat one. It has an in-depth look at second-order effects, so not only the P cap delta effect, but this P small delta effect. And pay a lot of attention to this B1 factor. And in fact, Dawn's going to talk about it next week. But firsthand, the students sort of come in and they take a look at different scenarios, like I'm showing here, different loading conditions, and we start calculating what the change in moments were as a result of second-order effects, whether it be the small P delta effect or the large P cap delta effect. If we're focusing, let's say, on the small P delta effect, we know that the B1 factor should be able to get pretty close to that, but it is an approximation versus the computer, which is going to be giving us the quote-unquote the exact solution. So we can compare these numbers. And so here is an example that the student might do. They've got moments on the end. On one end, they've got 150 kips of moment. On the other end, 200. They're also subjecting this beam to an axial force. And doing a computational analysis, they can calculate that the difference between the first and the second order moment is a factor about 1.96. And then over on the right, I sort of work through the AISC math for calculating a B1 factor. And in this case, they would get a factor about 1.8. And so again, just giving them an opportunity to try out the second order elastic analysis features and also do it for a reason. And this reason is to sort of check in on the accuracy of the AISC B1 factors. All right. And so different moment ratios will give you different results. And again, the student is also seeing that, the closer the axial force is to the elastic buckling load, the bigger that moment amplification term is, and also the bigger the difference between what computational analysis will give you and what the B1 factor will give you. And again, next week, Dawn's going to really dive in on these B1 factors for you. And we can create, this is another table out of the commentary, another figure, and on top of it we can superpose the masthead results and see what's going down. Learning Module 8, now this one is a pretty advanced one, but fun. Now we did a study that looked at the strength of columns, a study that looked at the strength of beams. Well, now in the virtual world, it's pretty easy for us to do beam columns. So we're going to subject the member to both axial force and major and or minor axis flexure. And like I said, if those two were sisters, then this would be the mother to that one. So again, looking at all different possibilities of major and minor axis bending and axial force. And how does AISC handle this thing? They handle it through an interaction equation. So what we can do is use masthead to calculate the actual buckling capacity or the actual strength according to a second order inelastic analysis, and we can compare our results. And so here would be kind of a plot a student could do comparing, it looks like I'm comparing the major axis capacity, the interaction of major axis bending and axial force, and having a look at and I also do provide the students some more advanced computational, the ADINA results, and they get a feeling for, AISC is doing a pretty doggone good job here. This next slide is actually pretty amazing. This is the interaction of axial force and minor axis bending. And when you plot the results of the AISC interaction equation against what masthead would calculate on a strength basis, it's actually amazing how an equation as simple as the AISC interaction equation can get that close. So some neat results to see. The last one is shifting over and looking at a design by the direct analysis method. So this course, of course, is about the direct analysis method. And so what this learning module actually does is it would guide you through how to design a small frame, or at least check a small frame, according to the rules of the direct analysis method. All right. And not only, I think once you see what Dawn's doing next week, the direct analysis method has a couple of variations on how to include initial imperfections and residual stresses. You can either do it directly, include the initial imperfection and use a tau factor, or you can do it indirectly by using what we call equivalent notional loads. So this learning module, you would do both and compare the results. And of course, you could also compare it against what a full-blown second-order inelastic analysis would predict, and that would sort of be an Appendix 1 type of check. So here we are in MassTan, and in the sort of screen superimposed in the front is the frame that would be looking at. Now, I did purposely in this learning module rotate the columns so they were subject to minor axis bending. The nice advantage of doing that was I get some pretty decent second-order effects, so we can actually have something to talk about. And again, we're looking at direct modeling of the imperfections or use of equivalent notional loads. And we can either check the design for a given amount of force, or we can go the other way and determine how much force we could put on here before we'd violate the specification. Now I'm going to drop back out into MassTan one more time, and I just wanted to show you the kind of fun you can have with MassTan in second-order effects and frames. So this is sort of a combination of the two learning modules, learning module number 9 and the early one on second-order effects. So let's see how we do dropping into MassTan. Okay. I need to open up that file. Okay, so I'm hoping you can see this fairly well. Maybe what I can do is just turn up. I may have made them too large. All right, so I increased the size of the arrows. The green arrows are the forces, and I have two frames here in parallel. The frame in the back has no gravity load on it, and the frame in the front is identical to the frame in the back, except it has gravity load on it. Okay, and so if we do a first-order elastic analysis, so that's the first option, and we run the analysis pretty quick, and then we'll come over and look in the diagrams, and we'll have a look at, say, the minor axis bending. That's what would be occurring in the columns, and plot up the moment diagram. What you can see is that there is no difference in the moment diagrams. So this gravity load, this axial force in the columns, is not being reflected. The second-order effects are not being reflected. Why? Because we did a first-order analysis. All right? And a key value to note is that the moment, just due to the lateral load, looks like around 720. So now we're going to come back over and we're going to actually do a second-order elastic analysis. And again, it's not rocket science. I'll hit the apply button, and in less than an instant it was done. All right? So these second-order analysis programs are quick. If we go to results and diagrams and moment Y, we can plot this moment diagram up. And now we have sort of some interesting results. In the back, just under that horizontal load, the moment's still at 722. But now when we introduce gravity load on the front column, the moment does actually jump. And it jumps because of that second-order effect. And we've captured the second-order effect by doing a second-order analysis. So the moment went from 722 up to 1042. So I've got some slides for you, screenshots that I saved of that, so you would have them in your notes. And so there we are when we did the first-order elastic analysis. There were no second-order effects modeled or included in the analysis, so the gravity load, that vertical load on the front frame, had no impact. We got the same moments in the columns. However, if we did a second-order analysis, now the moments are significantly different. By introducing the gravity load, we went from 722 without it up to a minor axis bending in those columns of 1042. So that's a 44% increase due to that, what we would call a P-cap delta effect. All right, so you're feeling it, you're experiencing it, as opposed to me just telling you this is what's going to happen. Like I said, Learning Module 9 is going to guide you through the direct analysis method, and it does this by actually prompting you to fill in these tables. Learning Module 9 has some other fun parts of it. It would require you if you went to the More Fun, to actually also design the frame or check the design using the effective length method. And what's kind of curious about this one is you'll recall that frame was pinned at the bottom and had a beam at the top. The direct analysis method, you just default to a K factor of 1, and it would give you a capacity of 603. The effective length factor, the K factor, is actually up above 2, and you have a significant reduction in the capacity. You're down to 275 in the compressive capacity. So it seems like the direct analysis method suddenly provided all that additional compressive strength. But of course, like I was showing in Lecture 1, you're also now increasing the moments because you have to increase the imperfection, and you also reduce the stiffness by a 0.8 tau. So you get some real fun scenarios going here. All right, so let's start wrapping tonight's lecture up. I've tested them not only in my classes for the last 3 years, but I've also talked to other instructors both in the U.S. and around the world who are using them, and students are appreciating and learning more about structural stability. Like I said, I've sort of got a bunch of things for you here that we went through tonight, but again, the whole thing is really the last one, in which you're getting a hands-on approach to learning structural stability and nonlinear analysis. I was hoping to continue to develop modules. If I can ever slow the folks down at AISC from keeping me so busy with the specification work, I'd like to sort of look at ones with leaning columns or bracing. Perhaps you've got some ideas. Certainly email them to me. I'd love to hear from you. Another piece of software called CU-FSM is a program that was developed originally up at Cornell, but now finds its home at Johns Hopkins University with Professor Ben Schaefer. And this would be an opportunity now if you wanted to look at local buckling and slender cross-sections and the combination of local buckling and sort of member buckling. You can't model an entire system here, but you can certainly model beams and columns and also see the interaction between local buckling and member buckling. All right, so you've got some neat options there. And that software, by the way, is also free. So go ahead and Google CU-FSM. All right, so we've gone through them all there, Ben. I'm sorry, not Ben Brent. Ben Schaefer is the one that provided CU-FSM. I think I just sort of, it's now up to you to give them a try and certainly change them up whatever you want. And you don't have to do them all. Just do a few, and then you'll be addicted, I'm sure. So some questions, but first I should just let you know next week Don White is going to take over, and he's going to his first lecture is really going to focus on taking this second order elastic analysis and taking a real look at the details. And so, all right, so maybe you still don't want to do a full-blown second order analysis. You still want to play in the B1 and B2 world using the moment amplification factors. Well, he's going to show you the details that you need to be thinking if you're going to go that way, or he'll also show you some details if you finally say, all right, you know what, let's just do a second order elastic analysis and use the program. All right. So that's what's coming. I always like to show this picture, Brent. It's my neighbor's barn. Of course, right now it's covered with snow. But when that barn was built, it was very stable, but those trees weren't there. And over time, the squirrels dropped some nuts and trees grew. That barn would have fallen over years ago if it hadn't been for those trees that have now grown and act as its lateral system. So I guess if you're having a structural stability problem, it's never too late to start planting some trees. So Brent, I'm going to turn it over to you. Sorry for going a bit long there, but I do think we might have a few minutes for some questions.
Great. Thank you very much, Ron. We'll try to get through some of these questions before we wrap things up tonight. I'm going to drop back to learning module 5 first. First question, this is back, there we go. Learning module 5, is there a method of modeling loads going away from the shear center?
Okay. Without really kind of rolling up the sleeves and getting into it, again, Mastan is going to take the easy way out and assume that the centroid and the shear center are at the same location. All right. If you trying to wing it or is difficult, my advice is not to go there, but to actually graduate to a different program, or even the use of shell elements and trying to model whatever the problem is you have at hand.
Okay. Can you go to slide 64, please? And again, we're in Learning Module 5 here.
Yep.
Can you please clarify the buckled shape?
Okay.
The beam cross sections are twisting all in the same direction with a point of inflection at midspan? Question mark.
Okay.
There is no brace at the midspan.
Okay, correct. So first, there is no brace at the midspan, but what there is for sure at that midspan is an inflection point. Okay. If we start from the left end over here, we've got bending moment being applied so that the bottom flange is in compression. And what happens is somewhere along the span, and I just provided a couple of these dummy elements for you, you can see the bottom flange is buckling and twisting the section. The top flange is in tension, the bottom flange is in compression. It buckles and the section twists. If we go to the other end, we've got load on here, and now what's happening is the top of the beam is in compression, so the top flange is buckling, and the bottom flange is in tension, and we're getting sort of that twisting to occur. So that's probably about as much details as I can give you at this point of what we're seeing there. It would be a little bit more fun if we could see a little bit, had more elements and we could see more of the actual twist profile along the length.
Okay, here's a general question about mass stand. Can the force value labels for applied loads be shown in mass stand?
Yeah, unfortunately I don't have that option. I can show on the moment diagrams and the like the values, but not the forces. So no, not an option there. Maybe I'll squirrel it over here as a thing to add to mass stand. When Bill McGuire was alive, we had sort of the goal of keeping mass stand as simple as possible and as user-friendly as possible. So every time we would come up with a neat feature, how about a feature that automatically generated an arch or something, we would argue it to death of whether it was worth including that feature because it would be one more menu pull down and the like. I do like that idea of being able to show the value, though. That's not so complicated to do, and I'll pencil it over as a thing to do on my to-do list.
Okay. Can we move to slide 72, please? The question is, why are the applied moments shown in different directions? Okay.
So we're talking about the top beam, and on both ends, all right, the moments are actually counterclockwise. So I would say these two moments are in the same direction, and if they're in the same direction and they were the same amount, then the ratio of M1 to M2 would be a positive 1. If we were to show, let's say, one in one direction counterclockwise and the other in a clockwise direction, then the ratio would be a negative value. So I'm not sure if there's some confusion there, but that's sort of what's going on here. And it's consistent with the way the AIC specification is taking these ratios.
Okay. And then let's move on to Learning Module 8, say 77. Sorry, maybe 76. So the first question is, Learning Module 8 used ETM. Can you define ETM, please?
Okay. So ETM is a device. Well, good for that person. I don't know who's already doing their homework out there, but that's great. So Mastan uses this plastic hinge concept, and so what I developed was the ability to reduce the modulus of the cross-section to account for partial yielding. So it's a sort of an ad hoc way, similar to the taw factor. The taw factor reduces the E value based on axial force. The ETM is really a taw factor that's reducing the cross-sectional stiffness based on both the axial force and the amount of bending. So giving you that quick answer, I do have a paper or two that I could provide you we could send on to that questionnaire, and so that they could sort that out.
Okay. And then next question on Module 8. Can you go to 81, please?
Okay, so this is actually 9, if that's okay.
Okay, I might be confused by the question. I thought the question applied to that slide, but let me go ahead and ask it, and maybe we can
sure.
verify what we're talking about. Please explain again why the columns were oriented for weak axis bending.
Okay, so it is this one. I could have oriented them for strong axis bending. The reason I did minor axis bending is really twofold. One, you naturally get a more flexible frame when the columns are bending about the minor axis, and so I was looking to make sure I had some decent second-order effects in there, so learning would be accentuated. The other thing about rotating those columns is I'm having the student check the columns. They're actually beam columns, right? And I didn't want them to have to worry about lateral torsional buckling of the columns. And so the check, by rotating them, a section subject to minor axis bending doesn't laterally torsionally buckle. An I shape subject to minor axis bending only either fully yields or is fine. So you don't get lateral torsional buckling when you subject a member to minor axis bending. So there were sort of two things I was after there to keep this problem simple enough so the student could get the big picture and the understanding.
Okay, and can we move to slide 54, please?
These are great questions, man.
Okay, slide 54. Why is it that we have one beam curve for in-plane and out-of-plane moments? Don't we need to have different curve for each direction? Do we not need to have a different curve for each direction?
All right, so for major axis bending, all right, so let's take the major axis bending of an I shape. It can fail in basically two modes. One, you could fully yield the section, form what we call a plastic hinge, or the second it could fail in lateral torsional buckling. And if you've got some yielding, then you've got inelastic lateral torsional buckling, and if you don't have any yielding, you've got lateral torsional buckling. So that's a member subject to major axis bending, and you would actually have this beam curve. Okay. For a member subject to minor axis bending, you will not have a failure. Let's start again. For an I shape subject to minor axis bending, you will not have lateral torsional buckling occur. So for a section subject to minor axis bending, an I shape subject to minor axis bending, you'll always be able to reach the full M sub P. And so I hope I'm answering the question, but the curve that I'm showing here is the nominal strength for major axis bending of an I shape. Now, if you have a section that you have both major and minor axis bending, let's say no axial force, but major and minor axis bending, then again you would find yourself in Chapter H of the specification, and you'd be looking at an interaction equation, but kind of a fun one in which this case you don't have any axial force, but you do have major and minor axis bending, and the interaction equation has those terms, and you're often checking it.
Okay. Will Mastan handle steel box girder sections?
Yes. So what you would need to do in Mastan, again, it's not going to capture local buckling, so web buckling or flange buckling in these box shapes. But if they were stocky enough, let's reduce the problem to a simpler one, and that's just HSS shapes. Then yeah, Mastan's going to be quite happy with that doubly symmetric shape, and you can either pick off the database if it's an HSS shape, or if it's like you were saying, a box shape, a unique shape, then you would need to calculate the plastic section modulus, the Z values about each axis, and input those into the program. So yes, but again, with the warning that you're not going to, when you go through and see the failure mode and all of that great stuff, let's see, I just lost my screen. Did you just take over, Brent?
Sorry, I did that. I apologize.
Okay. So when you sort of shift over, you're not going to get the local buckling from occurring. So Mastan will not detect local buckling.
Okay. All right. Well, thank you very much, Ron. I know there's a lot of questions, and appreciate you taking the time to answer those.